a mass spectrometer and the mass spectrogram. The instrument we use to measure masses of atoms is called a mass spectrometer. And the diagram of the mass spectrometer is over here. This is how it works. A sample is injected into the mass spectrometer. It's vaporized, and then it goes past an electron gun which ionizes the material. So it's now charged particles. When the charged particles are passed through a electric field, then they get accelerated, and so we've got fast moving ions moving into this magnetic field here. Now, particles that are too heavy don't get bent very much by the magnetic field, and they just basically go straight on and crash into the side of the instrument like that, and they don't get detected. Particles which are bent just the right amount bend around in a curve and then come down here into the detector, and they get detected. And particles which are very light, they get bent around too much, and they get bent and they hit the side of the instrument on this side, and they basically crash out and they don't get detected. So by adjusting the strength of the magnetic field, we've got electromagnet here. We can adjust the electromagnetic field there, or we can actually adjust the speed of the particles with the accelerator over here. So we can control that very carefully, and the particles come down into the detector. We can actually figure out how heavy the particles are. Now, mass spectrometer is an instrument that can actually sit on top of a desk these days. They used to be much larger, but they've miniaturized them, and that's what we get. Now, the graph that comes out of the mass spectrometer is a mass spectrogram, or it's a graph basically, that it's a graph like the one below. And you'll see this graph here. It's got percent abundance on this side. Well, sometimes this actually isn't labeled. It's just how much comes out basically. And the total of the two peaks here, this peak here plus this peak here, has to add up to 100%. You can see the two peaks, and down the bottom we have the weight basically. It's a mass to charge ratio, but we can figure that out, and that means the mass of the particle, and that peak there is at 35, and this peak here is at 37. And we physically, well, you can use maths to do it, but basically we measure how tall this peak is on the graph, and that peak comes up to be 3 times bigger than that one. So that whatever that peak there is, that one is 3 times the size. So we can soon figure out that the large peak represents 75%, and the small peak represents 24%. So we've now figured out that isotope 35 is 75% of the total, and isotope 37 is 24%. So one possible test question would be, you might be given a mass spectrogram, and you have to work out the percentage of each one. Basically you just measure it with a ruler and figure out what the ratio is. So if the numbers add up to, say you measure one of those, and it's say the big one is 15 centimeters and the small one is 5 centimeters, that makes 20 centimeters overall. So the big one is 15 over 20 times 100 equals 75%, and the small one is just whatever is left over, which is 25%. That's how you do that. Okay, now the next topic is the unit of amount in chemistry, which is the mole. Now before we tackle the mole, I just wanted to say that we have a way of measuring things in baking or counting eggs. Okay, take this stuff off. There we go. We've got a way of measuring things when we count eggs, and the measure that we use is dozens. Okay, so we've got dozens. When we count eggs, we use the amount of dozens. A dozen is a special name for the number 12. So how many, if I ask you, how many dozen is 24? Well, in your head, you would say, okay, 24, if I divide it by 12, that gives 2 dozen. I could give you any number, you would divide it by 12, and that will give you how many dozens there are. So we have a formula. The number of dozens is equal to the number of things divided by 12. Well, chemistry basically does the same thing. Exactly the same concept, but the numbers are a bit different and the names are different. So in chemistry, we do the same thing for atoms, but the special number is not dozens, the special number is moles. We call moles. And the number of things is not 12, the number is 602 hexillion, which looks like this. We've got 602, and that's basically thousands, millions, trillions, quadrillions, thousands, millions, billions, trillions, quadrillions, pentillions, hexillions. So that's 602 hexillion. Now, it's not very convenient to write 602 hexillion like that, so we have a different way of writing it. We write it as 6.02 times 10 to the 23. That just means 6 point, and then when you get to the point, you add 23 zeros after the point. So you get 02 plus another 21 zeros, makes it up to 602 hexillion. Now this number is a famous number in chemistry, and if you need to give a name for the number, we call it Avogadro's number. So our formula for calculating the number of moles, just like we had the number of dozens, is whatever the number is divided by 12 gives you how many dozens. So the number of moles is equal to the number of particles divided by 602 hexillion, Avogadro's number. So I'm now going to give you a quick question. Turns out there are about 1 billion trillion stars in the universe. How many moles of stars is that? Okay, I'll give you, just pause the video and see if you can work it out, and then I'm going to give you how I work that one out. Okay, you're going to need a calculator to do this easily, and I suggest you use the Sharp scientific calculator, which was on the book list. And we need to find our formula. So here's our formula here. The number of moles is equal to the number of things divided by Avogadro's number. So I'm going to write that in there. N equals N over Avogadro's number. And that's going to be equal to, now, there's 1 billion trillion stars. So 1 billion is 1, 2, 3 thousands, millions, billions. Is that right? Yeah. Just get that little dot off. Okay. So there's 1 billion, and then a trillion is going to be, let's see, thousands, millions, billions, trillions. Okay, so there's a billion trillion. We're going to divide that by Avogadro's number, 6.02 times 10 to the 23. Okay, got my calculator here and just tried to put the numbers in, and it didn't work. So I'm going to change that into 1 times 10 to the 21 divided by 6.02 times 10 to 23. Okay, let's try that again.